Hi, everyone, and welcome to Lecture 2 for E54. So today we're going to be talking about the structure of materials, and we'll see that there's many facets that comprises the structure of the materials that we care about. The first one in the first half of today's class, we're going to talk about how the chemical composition of the material matters. And really when we do this, we're going to be talking about atoms as the fundamental building blocks of materials. Okay. And with these atoms, you have to think about the chemical reactions that they undergo, how they form bonds, and how the bond formation is related to the electronic structure of the atoms, and how this ends up determining our properties of our materials and then other aspects of our structure. Okay. And just as a simple sort of way of looking at this, this tendency for atoms to bond together is what really gives us rise to condensed phases of matter. So the liquids, the gases, the crystals, the solids, the things that we're used to dealing with, these are what comes from the fact that atoms want to form bonds. So one of the first things to talk about if you want to think about the atoms that compose and comprise our materials is the periodic table. And this is just a way of presenting all of the elements that we know to exist in a way that has some periodicity, so we can have some predictive nature in a way that can predict the properties of the atoms. So first, we can talk about the fact that there are three primary trends on the periodic table. So the first thing we can talk about is the metallicity. So that this is the tendency of an atom to donate electrons to metallic or ionic bonds. And generally this trait increases as we go from top to bottom or from right to left, right? We can also think about the electronegativity. This is the tendency of an atom to attract an electron. And generally, this trend is going to go the opposite of the metallicity. So this is, metallicity is when an atom wants to donate electrons. The electronegativity is when an atom wants to attract an electron. And we can also see that there's going to be trends for size and mass. So as we go from top to bottom and right to left, we'll see that size and mass increase as well. Okay, so they follow the same trend as the metallicity. One thing that's worth mentioning is when we're talking about atoms, we can have both neutral or charged atoms. Charged atoms we're going to call ions, and a positively charged atom is going to be called a cation. Okay, now this is generally going to be smaller than the neutral atoms. And you can remember this by the fact that when we have a positive charge, we're actually getting there by taking away a negative electron, right? So we're removing something from the atom. In contrast, negative ions, which we call anions, are always larger than the neutral atoms. Okay? Before we dive in, let's sort of recall some basic atomic information that we probably learned in Physics 101. So the atoms that we're going to be talking about, they're made up of electrons, protons, and neutrons. Electrons have negative charge, protons have positive charge, neutrons have no charge. And one of the big things to remember is that protons and neutrons are much more massive than electrons. Okay, so we're talking about here the mass of each of these individual types of particles. The protons and neutrons are multiple orders of magnitude larger or more massive. When we talk about the atomic number of an atom, what we're really doing is describing the number of protons in the nucleus of the atom. Now, if we have a neutral species, so if the number of protons is balanced by the number of electrons, that also tells us about the number of electrons. Okay. On the periodic table, you'll also see atoms described in terms of their atomic mass unit, and we have to really define a baseline or a reference point, and an atomic mass unit is just 1/12 of the mass of carbon-12. Okay. You'll also see atomic weight on the periodic table, and this is just what's the weight of a certain number of molecules or atoms. In this case, it's Avogadro's number of molecules or atoms, and you can think of it as it's the weight of 1 mole of material, right? And there's an easy conversion. If you choose something that is 1 atomic mass unit per atom, that's its units, that's equal to 1 gram per mole. All right, so let's start digging into talking about the structure of atoms themselves. So one of the first models of what an atom looked like came from Niels Bohr. And this Bohr model of the atom had some things right and some things wrong. But anyways, it was based on this idea that a nucleus with the protons and neutrons was in the middle, and then you had these different orbitals that were moving out further and further away from the nucleus. It described the fact that we want to, when we talk about the number of protons, we're going to use Z, the atomic number. The number of neutrons is going to be N, and most of the atomic mass is going to be made up of those two particles. So the atomic mass is almost just the number of neutrons plus the number of particles, or sorry, the number of protons. And in this type of model, the first principal number we see is this quantum principal number. So it just tells us, are we in the first, second, third orbital set? And then we can also have different S and P and D type orbitals within that set. So it gets some things correct. It gets this idea correct that there's quantized energy levels. It also gets the idea correct that you can have electron excitation. So an electron can jump between these different orbitals. And when it does, there has to be some energy that's released. Okay. But it's not 100% correct. So it misses a number of things. I've just listed a few here. So it gets the emission spectra wrong for larger atoms. So it doesn't correctly predict how much energy is released. It misses the effect of magnetic fields on these spectral lines. It violates the uncertainty principle because in this picture, we are showing exactly where that atom is. So we're saying we know exactly where it is in time and space, which is a problem. And finally, this model would predict electromagnetic radiation loss that doesn't occur in real life. So all that being said, even though there are some problems here, our understanding of the atom moved forward quite a bit, and you still see this type of picture. So for example, in the Atomic Energy Commission, their original sort of logo had this type of model shown. So over time, physicists have improved their description of the atom. And one thing they've done is refine these models to make sure that they're capturing the wave-particle duality of the electrons inside around the that are part of the atom. And what this means for our discussion here is that instead of just saying that the atoms are at one distance from the nucleus, they're actually defined by orbitals that describe the probability of the atom or the electron being in a specific location at a given time. And then we describe these orbitals with quantum numbers. So in addition to the n, the principal quantum number we saw before, you can have these other ones. So for example, you can have a quantum number that describes the orbital that you're in. You can also have a magnetic quantum number and a spin up or spin down quantum number. And again, what we're trying to capture is the fact that charged particles have some properties that look like waves and some that look like particles. An easy way to see this is in this dual slit experiment. So if we shoot out electrons or something like that through a diffraction grating like this, which has two holes at certain spacings, what we'll see on our surface where we start to measure when electrons hit, we'll see that individual dots pop up. So this tells us there's some property like a particle. But as you go forward in time and continue this experiment, you'll see that there are some regions where you have constructive interference and other regions where you have destructive interference. And that's a wave-like property of the electrons. So just on the right here, what we're doing is we're showing contrasting on this left side of this figure, the original Bohr model. It said that we have an electron, it's in some orbital, it's a distance from the nucleus. And in terms of the probability, this was saying there's 100% probability that it's at a given location. There's 0% probability it's a little bit closer or a little bit further away from the nucleus. In reality, what we get is that there is a region of maximum probability, but it's non-zero closer to the nucleus and further away. So it's seen as a more statistical description of where that electron is. But some of the things remain the same. So the idea that we have these quantized energy levels that increase as we go up in terms of the principal quantum number remains. And those electron energy states are quite important. Generally, the closer an atom is to the nucleus, the more tightly bound it is. And what that means is that it requires a higher energy to remove. In this plot on the left, we're showing some of the lowest orbitals. And on the very left axis of this is the energy needed to break that electron away from this atom. And you'll notice it's quite a bit larger for the n=1 orbital than it is for the n=2 orbitals. Okay. And generally, these electrons are going to have discrete energy states, but they're going to want to occupy the lowest energy states they can. So what that means is as we move around the periodic table, we start adding more electrons and getting to different elements. We're going to originally start at something simple like this 1s, and we're going to start adding more electrons into these different states. So if this table right here is showing as we work our way down or sorry, up in increasing our atomic number, what the electron configuration is, how we're adding electrons into those different possibilities for the orbitals. And the point they're trying to get at, and the reason they're not showing it on purpose in the periodic table because they don't want to show that yet, but what they're getting at is that sometimes we have unstable configurations. So something like this, where we have one of the two spaces in the 1s orbital filled, but that means there's an opening, something that could be filled. And then every once in a while, we get a stable configuration. So something where that 1s orbital is completely filled. And you keep having some sort of repeating pattern of that. So we start to fill up those higher orbitals. Eventually, we hit something where it's filled, and those are stable. So if you go and look at which materials are stable, you get things like helium, neon, argon, krypton. These are actually what we call noble gases. And we don't call them that because they're royalty or anything. We call them that because they're inert. They don't tend to have chemical reactions with things. All this other stuff in between can have chemical reactions. So that actually serves as how we start to put together the periodic table. On this far right side, these are the elements which they have a completely full orbital and they're inert. They don't want to react with things. And all this other stuff, that's not true. And generally when we're on this left side, our atoms want to give up electrons, okay? And the number of electrons they want to give up depends on the column that they sit in. So this first column wants to give up 1 electron, it has 1 extra, second column 2, and so on and so forth. So these ones are going to give up an electron and become a positive ion. On this right side of the periodic table, it's going to accept 1 electron, accept 2 electrons, accept 3 electrons, and become a negative ion. On this slide, what we're showing is that same periodic table, but now we're actually coloring and giving a height to each of these elements based on its electronegativity. So the electronegativity is a tendency to want to accept those electrons. So we have higher values on the right side than we do on the left. And actually what you'll find is that oftentimes, not always, but oftentimes, we can have chemical reactions happen between materials with very different electronegativities. So in this case, this chlorine atom is missing. It has 1 space to fill with an electron. And the sodium has 1 extra electron. So these things will want to react with each other. And sodium chloride is a very common thing. It's just salt. We're also going to start digging into bonding. So many of the physical and chemical properties of the materials we care about are determined by their interatomic bonds. And generally, we're going to talk about a few different types of bonds. So we'll talk about covalent and ionic bonding. In one case, we're giving up an electron. In the other case, we are sharing electrons. Metallic bonding is when we have a metallic C. And then we also want to point out that those aren't the only types of bonding. So we will have some secondary bonding. Really what this means is it's weaker, things like van der Waals and hydrogen bond. And we'll go through these one by one. So the first one I want to talk about is ionic bonding. So that sodium chloride that I mentioned is a good example of this. So on the top left, we're showing that sodium atom. It has a full orbital here and then an orbital with just 1 extra valence electron. And if this guy can be shared, it can fill in that 1 empty space around the chlorine atom. Okay? If it does that, both of those atoms now have full shells. They're no longer neutral. Now the sodium has a positive charge, the chlorine has a negative charge, but they're happier because they've filled that valence shell of their electrons. Okay. Now, This does mean that there needs to be some sort of ordered lattice because sodium atoms need to be near chlorine atoms. And we'll talk a little bit today and more in the coming classes about the structures that these things form. But one important thing to note is that this is non-directional bonding. There isn't a sort of horizontal or vertical type of direction here. It's just that one electron has moved, they've been transferred. Okay. As I mentioned before, this generally requires a large electronegativity. So something wants to give up electrons, something has to want to accept it. And usually you'll see this in the metal wants to donate an electron. It's on the left side of the periodic table, and a non-metal wants to accept the electron, okay? On this bottom right is just showing before reaction and then after. And it's getting at that idea that you're taking two atoms, which by themselves are unstable, having them be near each other, and they become more stable as they have that electron transfer. Now, the first thing that you can do is try to describe what's the force or the attraction that's causing these atoms to get closer to each other and let them share these electrons. Okay. And we'll dig into that in a minute. So covalent bonding also happens when materials don't have enough electrons in that outer shell. But this one is a little bit different. So instead of one of the atoms giving up electrons to the other, when you have covalent bonding, you actually have sharing of electrons, all right? This is a good example for CH4. Both the hydrogen and the carbon atom want more because they have unfilled valence shells. But rather than one of them give electrons up, they actually arrange in some pattern so that you end up getting 4 more electrons around the carbon nucleus, okay? And it fills that outer shell. And you get 2 around that hydrogen nucleus, which fills that 1s shell around the hydrogen nucleus. Now, this happens, these actually have comparable electronegativities. So these, that's one thing that makes a difference here. And the other thing that happens here is you have highly directional bonding. So that's another difference between ionic and covalent bonding. There's many materials that have covalent bonding. Another good example is silicon. So this is actually just if you have pure silicon, so not different types of elements. All of these silicon atoms have a valence shell that's not filled, so they want to arrange in some pattern so that they can locally have enough electrons to fill that valence shell. Okay. On the right, and we'll talk again in more detail later, but on the right here is showing how they form this type of structure where each silicon is surrounded by 4 others that have some sort of prescribed angle and geometry to that unit cell. Silicon dioxide, or silica, is another good example. In this case, we have two different atomic species, a silicon and an oxygen. It actually has a structure which is quite similar to just the silicon by itself, but in this case, the silicon atom is in the middle and it's surrounded by oxygen atoms. Metallic bonding is the third major category. In this case, we actually are looking at a metal atom. It has, in this case, this is magnesium. It has 12 electrons overall. And you can think about it as an ion core, so the nucleus plus some of those electrons that's positively charged. And then there's those 2 valence electrons, those 2 in the outer shell. And magnesium and other metals will then arrange on a lattice so that they can share in what's called an electron C, all those extra electrons in the valence shell. And then if we look locally around a magnesium core, on average, you'll have enough that it will be locally charge neutral. Okay. So this is just another visualization of that. So these positive ion cores, this negatively charged electron C, and overall your material has a net neutral charge. Finally, we can also have secondary bonding. In this example, it's showing a polymer chain. So here you have a carbon backbone. There's hydrogen atoms coming off, and every once in a while there's a chlorine atom. Okay. So within this chain, we're going to have a covalent type of bond between, for example, the carbon and the hydrogen. But this chain wraps around, and as it wraps around, those side parts of the chain can interact with each other and also have a type of bonding that's called van der Waals bonding. So in this case, the positively charged hydrogen and the negatively charged chlorine are interacting with each other, and there's some bonding. Now, we call this secondary because it's not as strong as the primary bond. So for example, if I take this polymer and I start to pull on it, at first I'm not going to break these bonds in the backbone. Instead, I'm going to start to break these secondary bonds between the polymer chains. Now, it's important to point out some reality. So I mentioned this idea that there's three main types of bonding: covalent, ionic, and metallic, and then there's some secondary types. It's important to mention that these are sort of the models or the extremes, and it's possible to have bonding that shares some of these features. So, covalent is directional, ionic is non-directional. You can have something that's somewhere in between and shares some of the properties of covalent, some of the properties of ionic. In the same sense, you can have these mixed type of bonding between the other types as well. On the right figure on this slide, what it's showing is plotting different types of materials. So metallic materials, metals have metallic bonding. Things like semiconductors and polymers often have covalent bonding. Ceramics are all over the board, right? So they can be completely ionic, and they can be some mixture of ionic plus covalent. And then we can even find other examples. So we'll talk a little bit about these materials. They're sometimes called intermetallics. The individual atoms are metal atoms, but they're on some sort of ordered lattice. So there's some type of sharing of electrons happening. It's not completely a C like a pure metal would be. So let's look a little bit at that sodium chloride again. So we mentioned that the sodium atom is kicking out an electron and sharing with that chlorine one, and they're happy in that state, so they want to get close to each other and let that happen. If we just think about that action, so the fact that we're kicking out an electron and that makes the system happier, we could go and plot what's called the Coulombic force. That's what describes this type of reaction. And this would show that the force pulling these two atoms together actually gets higher as the atoms get closer. So as the spacing between them gets smaller, that force is going to get higher and higher and pull them together. Now, that's not the only part of the equation, though. So although that Coulombic force wants to pull these atoms really close to each other, we also know that at the middle of each of these atoms is a positively charged nucleus. And if they got too close, so let's say they were trying to be right over top of each other, you'd have a positive charge getting near a positive charge, things wouldn't be happy, okay? So on the top right here is a more complete picture of what's happening. This dashed blue line is that attractive Coulombic force, and that's a contribution. But there's also some repulsive force from the nuclei of the atoms as well. If we add these up together, we get this red curve. So this is the total forces that those atoms would feel. And what we can see is that when they're far away from each other, there's not much force. As you start to bring them together, they'll start to feel some force trying to bring them closer and closer together. Eventually, that'll hit zero and actually become negative. So if we're in this negative range, it means there's a force pushing them apart. It's actually repulsive, okay? So our system or atoms are going to want to find this 0 point. So they're going to want to find where they're no longer pulled together, they're no longer pushed apart, they're just in equilibrium. We can actually also take this force versus separation curve, and we could integrate it and figure out what's the potential energy of this, for now, two-atom system as a function of that separation. Okay. And this curve is going to look a little bit different. It's inverted in a way. But at that point where we had zero force on the atoms, we'll be at the lowest energy of the system. Okay. And that's often where our materials want to end up. They want to end up at the lowest energy configuration they can, or at the bottom of this potential energy trough. So just from bonding, we can start to get some material properties. Some really simple things can come out, like what's the bond length? So that's, what's that equilibrium atomic spacing? We can also get an idea of the bond energy. So how much energy does it take to break that bond? And if we think about it in terms of that schematic energy versus separation curve, it's going to be the difference between 0 and that minimum at the bottom of that trough. Okay. But we can also look at some practical material properties as well. So for example, the melting temperature is heavily connected to the bonding. Okay. There's a blue and a black potential energy curve here. And what this shows us is that as we maybe have stronger bonding, we can shift from this blue to the black curve. So it's a deeper well. Melting temperature is really just telling us, as I add thermal energy to my system, my atoms vibrate. When does that vibration become enough that it can pop the atom out of this potential energy well? Okay, so there's some vibration. When can I come out of this? And that's going to be related to the depth of that well. So this blue curve, which has a smaller bond energy, is going to have a smaller melting point as well. So that melting temperature is larger if that bond energy is larger. We can actually see that if we make a little table with some real material properties. So as the strength of individual bonds increases, the melting point also increases. But we do have to make sure to recognize that this statement is true just for a given bonding type. Okay. So here we have some examples for ionic covalent metallic and our two secondary type of bonds. Let's just look for now at this middle part. This is the metallic type of bonds. As we go down, our bonding energy increases. And we can also see that the melting temperature is going to increase as well. So the lowest one here is actually mercury. So this is a metal, but it's not in solid form at room temperature. It's actually in a liquid form. Okay? And we can contrast that with something like tungsten, which has a very, very high melting temperature. And we end up using this metal in high temperature applications. You can also start to see how thermal expansion coefficient is connected to the bonding of a material. This property, which we're going to call alpha, is defined as if I have some bar of material at temperature 1, that could be room temperature, it's going to have some dimensions. In this case, I'm going to track what the length of it is. As I heat it up, I'm going to find that the bar gets bigger, and this length extends out. So that thermal expansion coefficient is defined by taking what's that change in length over the original length, and it's the factor which we put in front, or the coefficient which we put in front of this T2 minus T1. Okay, so change in length equals alpha times the temperature change. Now this is actually also related to the shape of that potential well. Right? So if we had a perfectly symmetric potential well, like I show on the right here, and we added thermal energy, our atoms would be vibrating more. Sometimes they'd be more separated, sometimes less separated than the mean. But if it was perfectly symmetric, this vibration wouldn't really do anything. So our average position would stay the same. Turns out that real materials, that's not true. Instead of a perfectly symmetric well, there's some asymmetry here. And what you can see is that if we have vibration in here, my average position is not going to stay at exactly the same place. As I vibrate more and more, my average position is moving to the right, which means my atoms have larger separations and my material's expanding. And again, that's related to the shape of this potential energy versus separation curve. And again, if we have a larger bond energy, so that means we have a more intense curve here, this black curve, we're not going to see that effect as much. We're sort of deep down in that trough. We're not going to see huge variations. We're going to have a smaller thermal expansion coefficient. So in this case, thermal expansion coefficient is larger if the bond energy is smaller, so they're inversely related. You can see lots of practical applications of this. A commonly seen one is in railroad tracks. So these railroad tracks in both these pictures were originally straight. It was an incredibly hot day. These materials wanted to expand, but They couldn't because there was more railroad track in front of or behind it. So what they had to do is they had to buckle out to the side to allow for that expansion. You can also see this in bridges. So if you've ever driven over a bridge, oftentimes you'll see these expansion joints that are planned into that bridge. And this is coming from the fact that, so that we think about it as when we heat our material, it expands, but you can take that the other way. If we cool our material, it will contract and get, the atoms will get closer together. And that's actually very common in things like bridges when they freeze. So if a bridge freezes and the material can contract, it can sometimes crack and break the road or the bridge. If you have an expansion joint like that, it lets that expansion or contraction happen without leading to failure. So just a quick summary of bonding. We mainly talked about these three major types: ionic bonding, covalent bonding, and metallic bonding. And they change in some very different ways. So ionic bonds are non-directional, have a very large bond energy. Covalent are directional, and that bond energy can be variable. So some things like diamond will have a very high bond energy, some things like bismuth won't. Metals are non-directional as well, and they also have a very large variations within their bond energy, okay? Secondary bonding are the smallest energy, that's why we call them secondary, and these tend to be directional, okay? Now, we're gonna talk a lot about different classes of materials as we go on, and I'm just sort of giving you the first taste of that, is that metals have metallic bonding, ceramics either have covalent or ionic, semiconductors have covalent, and polymers have covalent plus secondary. In addition to what atoms are making up our system, we can start talking about different levels of atomic structure and how these atoms are arranged. So the first thing we can think about is something like a gas. This is argon shown here. In this case, there's no regular ordering. The atoms are just sort of loosely floating around space. Maybe they're held in their pressure tank or something like that, but there's no order to their packing. You can have gases which do have some order. On the top right here is showing water vapor. So this is H2O. So long range, there's no order. These are just gas molecules rolling around randomly. But if I zoom in and I find every time I see an oxygen atom, there's going to be 2 hydrogen atoms bonding to it. You can also get short range order in solids. This is a silica glass, which is showing how every time I find a silicon atom, there's going to be 4 oxygen atoms around it. But we're also going to see lots of times where we have long range order. This is sometimes called crystalline order. So the atoms are arranged in some repeating pattern. And what's cool about that is it means that if I have one big crystal of this material and I know where the atoms are in maybe the bottom left corner, I know that all the rest of the atoms are built up on that same lattice, and I can predict where atoms would be on the top right of this, whatever piece or part that I'm looking at. So we're going to have to talk about a lot of different issues when we discuss this atomic structure. We're going to talk about different types of ways that atoms can assemble into solid structures. We're going to talk about how density depends on the structure and how material properties vary in different directions when we have this ordered structure. On the bottom here, I'm just showing 2 ionic crystals, so cesium chloride and sodium chloride, which have similar types of structures. Although they look similar, they're not exactly the same. And we don't go over this today. We'll go over it more, I think it's tomorrow or in one of the coming lectures. And in this case, this is what's called a B2 structure, and this is what's called a rock salt structure. So just to see that crystal structure is very important, we can look at that silicon dioxide I've mentioned a few times. So of course, you can have different materials by choosing different elements, but even if everything is the same, if we have the silicon dioxide stoichiometry, we can have a material that's called quartz, or we can have vitreous silica. They're very different in terms of their density. They're very different in terms of their thermal expansion coefficient. So for example, the vitreous silica has a lower thermal expansion coefficient, but it's also isotropic. So as we heat it up, it expands equally in all directions, whereas the quartz expands more in one direction than another. And even things like the optical properties of materials, shown here by the index of refraction, can be different between these two systems. And that difference comes about in how those atoms are arranged. So quartz is a trigonal crystal structure, so it has that long range order. And vitreous silicon is what we call a glass, so it's a non-crystalline structure. Right? And as we really understand how these properties are different, we need to dig into how those atoms are arranged. This picture is just showing an example of a slice through silicon dioxide. On the left is a picture of what would happen with quartz, and on the right here is the glassy material. So you see that it's more disordered than the quartz. That atomic packing ends up being pretty important for energy. So we can take these potential energy versus separation curves and think about what a non-dense random packing would be and compare it to a dense ordered packing. And it's pretty simple to see that if we're not at that optimal atomic spacing, we won't be at the bottom of this trough and we'll have a higher energy of our system, okay? The main point here is that most materials really like these dense ordered crystalline packings, okay? So most solid materials we see are gonna form some sort of crystal structure. You can go in and classify these systems in many different ways. You can talk about how gases have no order. Amorphous materials have no long range order, but have that short range chemical order that we talked about. And then liquid crystals are something that's quite different. They both have short and long range order. And you'll also see, we'll eventually talk about things like single crystals, where we have one crystal and one orientation for our whole sample, and compare that with polycrystalline materials. We have many crystals making up our larger sample. So we can have lots of different types of descriptions of material structure. And the idea is that we need to describe how these atoms are connected on many different length scales. To see why that's a problem, all you have to do is take something simple like table salt, that sodium chloride, and think about, okay, well, how many atoms are in something that is more tangible, something that an engineer might care about? Well, in 1 grain of table salt, there's 10 to the 21 atoms. So what we often really need to do is describe different length scales of our structure. One of the first things we're going to do is talk about what is the ordered periodic arrangement that the atoms want to have. Okay, this is going to be what we call the unit cell, so how those atoms are arranging. Okay, one important thing to keep in mind, and we'll talk about it in coming lectures, is that's not the whole story. So this is a sort of representative unit and a recipe for how those atoms can combine. But if we take this unit cell, which just has a few atoms, and we put it together into a grain of salt, we're also going to see that there's imperfections from that unit cell as well. Okay. So today we're just going to talk about putting atoms together, but we'll end up having a lot of descriptions and ways to talk about how we have deviations from that perfect structure. Okay, so for the crystal structures, we're going to start with some simple ones. In this case, we only have one atom type. And these are actually things which I'll show you some specific examples, but we end up seeing them in many metallic systems. So on the top left, I'm showing you what's called simple cubic. So this is where we have a cubic unit cell. So it means that all these sides are the same length and all these angles are 90 degrees. And we have one atom centered at each corner of this cube. Okay. On the bottom here is just showing another way of visualizing that. So it's showing multiple cubes in a 3-dimensional picture. We have one atom at each corner. Okay. Body-centered cubic is just one step up in complexity. So you start with that same cubic cell. There's an atom at each corner, but we imagine that we also put an atom right in the center. So body-centered. Okay. Face-centered cubic is a similar idea. We have an atom in the corner of this cubic unit cell, and then we're going to put another atom centered on each of the 6 faces. I'm showing you the front 3 faces, but there's 3 more in the back of this unit cell. One thing we might need to think about is how many atoms are shared between these different unit cells, the way to think about this is if we have our cube and an atom is fully inside of it, it's fully contained within that unit cell. But if it's shared between two different cells, we need to split its contribution. So for example, if we have an atom that's centered on a face of a unit cell, you can think of it as half of that atom is belonging to this cube and half is belonging to the cube below it. When we have an atom at the corner, you can think of it as 1/8 is belonging to this front top right unit cell. 1/8 is belonging to this front top left unit cell, and so on. So 1/8 of that atom is in each of these cubes. So if we go back to those three crystal structures I just mentioned, we can see that in this case, we have 1, 2, 3, 4, 5, 6, 7, and then there's 8. We can't see it, it's the back left corner, atoms, and each of those atoms is shared with other unit cells, so it's 8 times 1/8. So there's one full atom contained in this unit cell. In the middle, we have something similar, so one full atom from those atoms in the corners, plus one atom that's fully contained, so 2 atoms total in that unit cell. In the face-centered cubic, we have one atom coming from those corner atoms, and then we have 1, 2, 3, 4, 5, 6 face-centered atoms. Divide those by 2, we have 4 atoms total in that unit cell. Oftentimes in these types of crystal structures, the atoms are close packed or touching along certain directions. So for example, in the simple cubic unit cell, these atoms are touching along these edges of the cube. Okay. Top is just showing it, just that unit cell. Here's showing just the front face with the 4 different spheres. In the face-centered cubic, the atoms are touching along the diagonal of that unit cell. And then finally, it's showing just how, for the body-centered cubic, the atoms are touching in a diagonal that goes through the cube. So it isn't just in the 2D projection, it's in, you have to look at the 3-dimensional picture of that unit cell. So it's going from the front top left to the bottom back right. So for the simple cubic structures, there's a little video showing that structure. This actually turns out to be pretty rare due to the low packing density, right? So of materials that are found in nature, only polonium has this simple cubic structure, and that's sort of an obscure element that we don't really use for anything, okay? So in this case, the close packed directions are along the cube edges. We can also look at things like what's the coordination number. If we take this red atom, we ask which atoms are closest to it. There's 6, so 4 in this plane, and then 1 above and 1 below that are equal spacing from it. Even though many elements don't form this structure, we could ask ourselves something, how can we describe that? A simple way that we can describe a crystal structure is what's called the atomic packing factor. Okay? This is simply defined as what's the volume of the atoms in the unit cell divided by the volume of the unit cell itself. So it's basically saying in this picture, how much space, what fraction of the space is filled up by the atoms. And you can, in contrast, say 1 minus the atomic packing factor is how much space is empty or free. So the way you can do this is pretty simple. So if we know how many atoms are in the cell and we know what size they are, just in terms of the dimensions of that cell, we can go and calculate this. On the bottom right is showing that calculation for the simple cubic structure. So the first thing we can do is ask ourselves how many atoms in that cell. Again, we have 8, but each of those is only 1/8 in this cube. So we have 1 atom per unit cell. The volume of that atom is going to be 4/3 pi r cubed. Now we don't want to leave it in terms of r. We want to actually put it in terms of A, the dimensions of that unit cell, okay? So we mentioned that these atoms are touching. So A one length of that unit cell is going to be equal to 2 times R. Okay, so we could put that in terms of A. And finally, the volume of that unit cell, if it's a cube, the lengths are A, it's just going to be A cubed. We plug that in, we end up finding that the atomic packing factor for simple cubic is 52%. So that means only 52% of the volume in this cube is filled up with atoms. Body-centered cubic, this is the one where the atoms are touching along the cube diagonals. So from the front top left to the bottom back right. This is actually a one that's commonly found in nature. So things like chromium, tungsten, iron, when it's in the alpha phase. We'll talk about different phases of a given element later on. Things like tantalum and molybdenum. So in this case, we have a coordination number of 8. The easiest way to see that is if we look at that center atom, its nearest neighbors are the 4 atoms on the top plane, the 4 atoms on the bottom plane. That's its 8 nearest neighbors. And again, we have 2 atoms, or sorry, 2 atoms per unit cell. We can ask ourselves the same question: how much space is filled up by this body-centered cubic structure? We'll go back and do it the calculation the same type of way. So first, we'll ask ourselves how many atoms per unit cell. In this case, there's 2, 1 contributed by those corner atoms and 1 from the atom in the middle. We'll again put in the volume of that atom. Again, we're going to want to connect the radius of the atom to the dimensions of the cell. And to do that, we can acknowledge that those atoms are touching along that diagonal. So this diagonal right here is where they're touching. First thing we can do is see that that vertical portion of this triangle that I drew is just A. So that's one of the lengths of the cube. And then we can use simple geometry to say, okay, well, the bottom diagonal should be square root of 2A, and this diagonal through the center of the cell is going to be square root of 3A. We can do that and replace R and say what the volume of that atom is in terms of A, the lattice parameter. And finally, the volume of that cube is just A cubed. Plug that in, we get that 68% of the volume is filled. So a lot better than that 52% we saw for simple cubic. I'm sorry. Face-centered cubic is where the atoms are touching along the diagonals of the cube face. So right here. Many common metals that we use in engineering, things like aluminum, copper, gold, lead, nickel, platinum, and silver have this type of structure. Its coordination number is 12, and we have 4 atoms per unit cell. Okay. So just like we did for all the other ones, we could go in and calculate what the atomic packing fraction is. Again, how many atoms are there in this unit cell? In this case, there's 4. 1 contributed from the corner atoms, and 3 from those atoms that are centered on the faces, so 4 total. And then we need to connect the atomic radius to the dimensions of the cell. I'll leave that for you if you're interested. Just basically using geometry to connect this diagonal to these 2 segments, which both have length A. Now, what's interesting is when we go and we calculate this, we find that 74% of space is filled. And this is actually the maximum achievable atomic packing fraction with solid spheres. So this tells us that that's probably why we see lots of different metals that we know in real life form this type of structure. One thing I want to point out is that you can't just think about where the atoms are in those cubes. You have to also think about what element you see there as well. So for example, I showed you cesium chloride earlier, and this is just redrawing it. So in this case, there's a chlorine atom in the middle, and there's cesium atoms in the corner. And if you look at that after those slides I just showed you, you might say, well, that's body-centered cubic. It has atoms on the corners of the cubes, and then 1 in the center. But that's incorrect, because body-centered cubic, all of these atoms are the same species. So they're all something like iron. In this case, there's 2 different types of atoms. This is actually a different structure. Now, We can also, we should just showed you and just talked about how face-centered cubic is the best way to pack atoms we can get to. It's important to ask ourselves if there's any other ways we can get to that same value. So one way to see this is we can think about, let's just start in 2 dimensions first. So rather than go to 3D and get complicated, let's just think about, okay, if we're looking at a 2D plane, we're putting marbles or atoms on that layer, how could we do it most efficiently? Well, the square type of lattice actually isn't that good. It has lots of empty space here. Instead, what we want to do is form this hexagonal lattice. So any one atom is surrounded by 6 other atoms in that plane, okay? So this is the best way we can do it in 2 dimensions. Now we can think about starting to build up a solid 3-dimensional material out of these layers. So if I start with a layer with that packing, I'm putting atoms at what I call A sites. I then can start to add on my second layer of atoms with that same packing structure. Now, if I put them right on top of the A atoms, it's not going to be very efficient. I'm going to have a lot of open space. Instead, what I want to do is put the atoms in one of these on top of one of these open spaces. Now, the reason these things are labeled differently is that if I put one atom here, I can't put one there. They would be overlapping. So if I put an atom at a B site, I need to fill in all the other B sites, okay? So this would be after I have that second row of atoms. Now I can actually just keep repeating that over and over and have A, B, A, B, A, B, so on forever. And this gives me another crystal structure. This is what's called hexagonal close packed. So in this case, we have this hexagonal unit cell. On the top, there's a hexagon of atoms, and in the middle, we're just having some chunk of that middle hexagon. Okay. So this also has that maximum achievable packing factor. But one thing I want to point out is nowhere on this slide does it say cubic. So we talked about simple cubic, body-centered cubic, face-centered cubic. Those all had a cube. Hexagonal close packed is a close packed structure, but it doesn't have a cubic structure. What I mean by that is, in addition to this hexagonal cell, I can also draw it as this box like this, okay? In this case, I have 4 atoms on top, 4 atoms on bottom, and 1 in the middle. And what I'm really doing is trying to capture some chunk of this unit cell, and then that little atom that's in there, okay? The difference is this is not a cube. So this height is not the same as these dimensions on the bottom. And also the angles aren't 90 degrees, okay? So HCP is not a cubic structure. Now, I mentioned this idea of I have atoms stacked in a layer in A positions, and then I put B on top. After I did that, I didn't have to go back and go A, B, A, B, A, B. I could have then put atoms at the C position. So I went A, B, C, A, B, C, A, B, C, and keep doing that forever. And in fact, that's actually the face-centered cubic structure. It's just from a different perspective. So when we were looking at that face-centered cubic structure, we said, okay, well, here's these atoms on the corner, there's some atom at the face. We were looking at it from a different perspective than how I would stack these 2-dimensional planes. So these are actually planes stacked at an angle, but they give us that same structure. So one thing we're going to have to do as we work our way through and talk about these different materials is define directions and planes of crystals. So I want to finish today with some basic crystallography. So when we talk about directions inside of these unit cells or inside of a lattice, we're going to define them in terms of the basis vectors. So in this cube, instead of calling it X, Y, and Z, I called it 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so those are my basis vectors. Now, if I want to describe something that's along the X direction, it would be in the 1, 0, 0 direction. In contrast, if I want to talk about something that's moving upward along this left face of that cube, this thing is moving 1 unit in the X, 0 units in the Y, and 1 in the Z. So it's going to be 1, 0, 1. That's this arrow right here. If I want to go through the diagonal of this crystal, it's going to be moving 1 in X, 1 in Y and 1 in Z. So it's 1, 1, 1. Okay. Now, you'll oftentimes find different things bounding these numbers. So when we use the square brackets, we're talking about a specific direction. And when we use these triangular brackets, we're talking about a set of directions that are crystallographically equivalent. Okay. What I mean by that is, let's just think about a simple cubic cell. If I had an atom on each of these corners, they were all the same. If I move from the back left bottom corner to the front left bottom corner, I'm moving from one atom position to the next. That's physically the same as if I were to move from this position right here over to the right, because I'm moving from one atom to the next. Okay, so there's a 1, 0, 0 direction, there's a 0, 1, 0 direction, and there's also a 1, 0, 0 type direction. So it would be all the ones that move me between atoms in the same way. We'll use something similar to talk about planes. So we actually describe planes by the normal vector. So this is a plane shown here cutting through this cubic cell. Its normal vector is coming up and to the right, okay? And we use, in this case, it's 0, 1, 1. I'm going to show you how to describe this for different types of planes. But here we also have to use different bounding descriptors. So parentheses talks about a specific plane, and the squiggly brackets talk about a crystallographically equivalent plane. Okay, so how do we find those descriptors for the crystal planes? It's pretty simple. There's an easy way to do it. You don't have to guess what that normal vector is. What you can do is you can actually first find where the plane intercepts each axis. Then you can take the reciprocal of each of that number, and then if needed, you find the smallest set of common integers. So let's go through this for a bunch of different examples. So on the top left, we have this plane at the top of a cube. So we ask ourselves, where does that plane intercept each axis? So it doesn't intercept the x and the y axis. So we're going to say it does so at infinity. And it intercepts the z axis at 1. Okay, so we have infinity, infinity, 1. Our second step is we take the reciprocal of each number. Okay, so that's 0, 0, 1. Right. So this plane right here is the 0, 0, 1 plane. We can't reduce it any more than that. So this is that 0, 0, 1 plane specifically that I mentioned. And when I talked about how we have different cubes above, below, back, behind, and to the right and left, you can also say that this is that exact plane, and these are equivalent 0, 0, 1 type planes. We can do more and more examples. So this is showing some plane cutting through diagonally through that cube. Here we can ask ourselves again, where does it intercept each axis? It does it at x equals 1, y equals 1, z equals 1. So 1, 1, 1. The reciprocal of that is 1, 1, 1. We can't reduce it anymore. And these are 1, 1, 1 planes. The top right, it's going at an angle through there. We can see that it hits the x-axis at 1, the y-axis at 1, and it never hits the z-axis. So the intercepts are 1, 1, infinity. We do the reciprocal of that, it's 1, 1, 0. These are 1, 1, 0 type planes. Final example, this example I'm showing you right here, it's intercepting at 1/2, 1/2, and 1/2. We take the reciprocal and we get 2, 2, 2. We can actually reduce that to find the smallest set of common integers. This would also be a 1, 1, 1 plane. Okay, and that's not a trick. The fact that these have the same index is true. We're cutting through the cube in the exact same way. Now, one important thing to point out is that when we talk about a certain type of plane, it actually can look different depending on the crystal structure that we have. To show this, I took an FCC crystal on the top, a BCC crystal on the bottom. I cut this diagonal plane through the sample for both, and these are both 1, 1, 0 type planes. Okay. And we can see, though, when we look at that 2D projection of the plane, the atoms are arranged in different ways. In the FCC crystal, the atoms are touching along the top, but there's a lot of empty space in the middle. In the BCC, the atoms aren't touching at the top, they're touching along the diagonals, okay? And this is actually a more dense packing in that area. Oftentimes, and the last thing I'll mention today is that we can sometimes talk about the density in different directions and in different planes. There's a few different ways to describe this. The first one is what's called linear density. So here you can just define it as the number of atoms centered on a direction vector divided by the length of the vector. So how many atoms am I crossing divided by the length? So for example, if I go here from position X to position Z, the number of atoms I cross would be 1/2, 1 and 1/2, so 2 total, and then divide that by the length of that arrow, right? You can do a similar calculation of density with planar density, and here you're just saying how many atoms are centered on a plane divided by the area of the plane. Okay? There's just two different ways to draw that. So for example, I could go here and say that along this direction, the top here, the linear density is very high, but this area density on this plane might not be that high because there's that empty space right there. In contrast, maybe the linear density isn't that high along this top direction, but in that plane there, in that area, most of it is filled up by atoms. All right, so that's it for today. I will see you all in the Q&A sessions. Have a great day.